I haven't really figured out where I'm trying to go with my sort of next idea with regards to prime numbers though. But I feel like there's an element of the definition of prime number that translates into the Collatz conjecture, which prevents us from finding the proof. You see, prime numbers can only be divided evenly by one in itself, but it's necessarily greater than one. So what we're doing is we're confining the definition of prime numbers to something that is not inherent to the number. It's an observational factor. You see, negative numbers are also all technically prime in that they fit all the sort of criteria of primeness that we find in the set of natural numbers, but they're necessarily excluded from the set of data because we can't use them to construct the numbers that we want. We want to construct positive numbers, as you can see moving forward. But the problem with that is that it's contingent on a forward moving sort of linear series of observations. So you're going to find an infinite number of prime numbers because you have an infinite number of non-prime numbers, and you have an infinite number of negative numbers that could be prime that we've already excluded from the set of data. And I feel like that's part of why the Collatz conjecture is so hard to find, because part of the Collatz conjecture is again that positive integer. So we're necessarily using something about primes, but we don't actually have a formalized definition of prime numbers that actually defines what primeness is, because what part of a number is prime? What part of 2 is the prime part of 2? Because 2 is even and 1 is odd. So we already have, it's not basic with even and odd with respect to that. And it's also not with respect to its positivity. It might be with respect to positivity. There might be something to do with positivity with primeness. But I would propose that if you eliminated all positive numbers instead of negative numbers, then you would have an infinite number of primes, which is exactly what we suggest in the positive scape. But that's just because, again, our definition of prime numbers necessarily excludes that. So I'm trying to work on that. But yeah, when you say that there's division in the Collatz, when you say there's multiplication, technically there's addition, because multiplication and division is addition. So that's all of the general things that you can do with numbers, at the very least in an algebraic sense. But, you know, if we're dealing with a transcendental property of numbers, or if we're dealing with a property, what I consider transcendental is something that has to do with the observational metric that you use a number in. For example, pi. This is an observational sort of metric. Pi is a ratio that you can see between a circle circumference, which is the area that it encloses, a two-dimensional area, and the distance across that area. It's a natural sort of ratio based on an observed phenomena. And that's the same thing that's going on with prime numbers. It's an observed phenomena that if you try to look for the numbers that fit specifically this definition, you will find specifically this set of numbers. But technically, you can change the definition to be anything you want, and that's a contradiction, sort of. Not really a contradiction, really, but it's kind of a suggestion that primeness is a transcendental factor, in that it's observational and not necessarily inherent to a number and its ability to interact with other numbers. So that's just what I want to talk about right now.